Graph plotting is a pretty common interview question in IPhD and PhD physics interviews. So in this video, we'll try to discuss every kind of questions that comes and the following follow-up questions that might be asked. So start with the broad steps that we will need to plot any kind of function. First is to identify the even and odd functions, whether a function is even or odd. What is the condition for even function? If we put a minus x instead of my instead of x in the function, then we should get back the original function. For example, it's y, if fx is x square, then if we put minus x instead of x, then what should we get? Minus x square, which is x square, which is the original function. So f of x equals to if equals to f of minus x. So this is the condition for even function. And even function, if you plot an even function, then it and if we reflect the function on the y-axis, it looks identical. For example, if this is the x square function on the positive x-axis, and then we just need to reflect this on the y-axis, so we should get the behavior on the left axis also, like that. And odd function, the condition is that fx equals to minus of f minus x, which means that if we put uh, minus x instead of x, then we should get a negative sign in the front. For example, it's x cube. If we put minus x in places of x, then we should get this, and this is minus 1 cube x cube, and this is minus 1 x cube. So so this is minus x cube, which is exactly equals to minus of minus x. So this is an odd function. So now if we plot this function, then it behaves a little bit different. What happens is that if we plot on the right hand side, on the positive x-axis only, then what we need for plotting on the left axis or the negative y-axis, we just need to flip it on the y-axis, on the x-axis also. So we'll get something like this. The next step is to The next step is to find the zeros of a function, which means where the function goes to 0. For example, if y is x square minus x, then where does this function go to 0, or where the value of this function is 0, which means is if we put equals to 0, then we can write x minus x into x minus 1 equals to 0, which means x y is 0 at x equals to 0 and x equals to 1. If we plot it like this, then we can say that the function cuts the x-axis at x equals to 0 point and x equals to 1 point. Another example would be exponential 1 by x. at maybe uh, let me make it my exponential minus 1 by x. So what happens is that what at x equals to 0, what happens? Exponential minus 1 by 0, what is this? Exponential, this is minus infinity, this is 1 by exponential infinity, which means basically 1 by infinity equals to 0, which means at x equals to 0, this function is the value of this function is 0. So we will mark this point. This will be important in later steps. The next step is to find the values of the function at x equals to 0, at plus infinity and minus infinity. Very important to note here is that if the value of the function goes to infinity or minus infinity, at x equals to 0, just above x equals to 0, then it's important to find what happens at x equals to 0 minus also. 0 minus means a little bit less than 0 value uh, at x equals to 0, less than x equals to 0 but close to 0. For example, let's say this point. Okay, so because we'll see interesting phenomena, behaviors of the function if the function diverges at x equals to 0. Then we'll go for what happens at plus infinity and minus infinity also. I'll solve some examples. Only then I'll be able to explain more, so we'll do that later. The next step will be to find maximas and minimas of the function. How we will do that? We'll set the derivative of the function at 0. We'll find the values of x, which we'll name x naught. These are the points of maximas and minimas. Now if d2y by dx square goes to plus infinity, goes to gives some value that is positive at x equals to x naught, if the double derivative of the function gives a positive value at x naught, then the x naught is a point of maxima, or the concavity is upwards. And if it gives negative value, then x naught is a point of minima, which point of maxima means the function will be like this is x naught, and minima means it will be like this
Before
is point of
going
minima.
any further,
Okay, before going in details, let's go through some basic functions like ln x. How does it look like? It looks like this. Let me change the color. It looks like this. Okay, and this is ln x, this is x. Log x looks similar, but there's a slight difference. That's you cannot just distinguish like that. So let's move on to Desmos to see how does it look. This is ln x and this is log x. Okay, so the blue one is log x and the red one is ln x. So the thing is that both goes to infinity at x equals to infinity. Okay, both of them at x equals to plus infinity. Now then comes 1 by x, very basic. This is the y-axis. So the plot looks like this. Okay, like this. How at x equals to plus infinity what happens? One, it goes to 1 by infinity. It's basically 0, and and at x equals to minus infinity what happens? 1 by minus infinity, it's basically again minus 1 by infinity. So no, so it's minus 0, so it's basically 0, but it approaches from the negative side. At x equals to 0 what happens? uh, it it's basically 0 plus, because I as I said, if at 0 what happens, it diverges. So it's always clever to see what happens on 0 minus, right? 0 minus means that a little bit less than 0, so we'll put a minus sign on the before the function, and we'll see 0 at x equals to 0, so it's minus infinity. Okay, so it goes to minus infinity at 0 minus, and at 0 plus, which is 0 plus is basically at little bit at just away from x equals to 0, but on the plus side. At 0 plus it goes to plus infinity. Okay, a basic concept that we need to learn is that the shifting property. If uh, if there's a function, let's say 1 by x, how does it look like this, right? Then if we want to plot x minus 1, what we will do, x minus 1 means we'll shift the curve by 1 units towards the right, by 1 units because it's 1, and towards the right because it's minus. Okay, if we had written x plus 1, we'll shift the curve towards left by 1 units. So the x plus 1 would look like this, x minus 1 would look like this. Sorry, let me correct it a little bit. It will look similar but like this. Okay, and the x plus 1 would look like this. This is 1 by x, this is 1 by x minus 1, and this is 1 by x plus 1. Okay, so let's go to Desmos. So we'll switch it off. 1 by x is this, then 1 by x plus 1 is this. It just shifted on the right side, on the left side, and 1 by x minus 1 looks like this, which it got shifted on the right side. Okay, now as uh, I hope you realize that I made some mistakes, but we will figure that out. We'll correct it when we'll uh, do the plotting of the functions in details. Okay, so just for the sake of convenience, um, the x plus 1 kind of looks like this because it did not shift much, right? So like this, and x minus 1 like this. Similar thing, we'll do that in details later. Okay, okay, shifting. Okay. A very important thing to note here is that the coefficient of x should be 1, then only this logic works. If it's not 1, let's say 1 by 3x plus 4, then we cannot say that the 1 by x curve is shifted by 4 units. It means that the 1 by x curve is shifted by 4 by 3 units, because what we'll do, take 3 common and make the coefficient of x as 1, and so we'll have to do this, we'll have to take 3 in the denominator of 4. Okay, so the shift is 4 by 3 units. A complicated example would be that of sine, let's say 3x plus pi curve. Okay, how does sine 3x look like? Just sine 3x, it looks like, so look, sine x looks like this. Okay, since it's 3x, which means the frequency is tripled, what means is that it will be like this. If this is pi, this is 2 pi, right? So the curve will look like this. So the frequency is tripled. It crosses the x axis 3 times between 0 and pi. Okay, okay. Now if we want to shift by pi, shift 3x, we will have, if we want to plot, this is sine 3x, this is, sorry, sine x, this is sine 3x. Now if you want to plot sine 3x plus pi, then what we'll have to do is that we'll have to shift sine 3x by unit of pi by 3. For to make the question easy, we'll do minus pi, because shifting on the left side we'll have to draw again. So let's make it minus pi, and here also. So we'll shift the curve by an unit of pi by 3. Okay, pi by 3 on the right. Okay, so how will it look? This is pi by 3. This was pi. This is the pi line. So pi by 3 would be this line. This is pi by 3 line. We'll shift the curve by pi by 3. So this is 2 pi by 3. This is pi. Okay, so we'll start this curve. We'll just shift this curve by and start from this position. Okay, so this makes this is let's make it more clearly. Okay, so we'll start from here. This, 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 and so on. Okay, so and we'll for continuity we'll do this. Okay, so basically this is the same curve, just shifted by pi by 3. Okay, so we'll get 3x minus pi. Okay, let's go on Desmos to make it clear, because my handwriting is not good. So if we do sine x, it looks like this. If we do sine 3x, it looks like this. Let me make x mark that pi and pi by 3. Okay, so it does mark like that. X equals to pi by 3. Okay, now if we do sine 3x minus pi, then what happens? This black curve just moves. Sorry, this is sine 3x minus pi. So this black curve just moves by an unit of pi by 3 to the right. So we'll start this black curve from pi by 3. So we'll get the same function again. Okay, to make it more intuitive, let's do it this. Let's do, add an n. Okay, so if we keep on increasing, let's start from 0. If it's 0, then it's basically sine 3x. Okay, uh, sine 3x. Now if we just keep on increasing, uh, keep on increasing, at the point n equals to 1, which is pi, which is sine 3x minus pi, we'll see that we get the required function sine 3x minus pi. If we again move back to 0, which means sine 3x, then we'll see the green curve moves to the left and it merges with the sine 3x curve. Okay, so it's just shifting of the original function. Got it? Let's learn how to plot hyperbolic functions. For hyperbolic functions, it's simple. We'll first write the hyperbolic functions in terms of the exponential forms. For sine hyperbolic x, we'll write this as e power x minus e power minus x by 2. Okay, at x equals to 0, what happens? At x equals to 0, it's 1 minus 1 by 2, so it's 0. So if you plot it here, at x equals to 0, the function is 0. At x equals to infinity plus infinity, what happens? It's e power infinity minus e power minus infinity divided by 2. This goes to infinity, this goes to 0. So the result is it goes to infinity. At x equals to minus infinity, it's power minus infinity minus e power plus infinity, because there's already a minus, so by 2. So this goes to infinity again, and this goes to 0. So the result is minus infinity. So the graph will look like this, right? And again, yeah, this. Now if we want to plot cos hyperbolic functions, we'll do this in a similar way. E power plus e minus x by 2, and this is an even function, so we'll just figure out how it looks like on the right axis, on the right positive x-axis. Okay, so at x equals to 0, what happens? The function is 1 plus 1 by 2, right? So it's 1, so like this. And at x equals to plus infinity, what happens? It's infinity plus 0 by 2, so it's infinity. So it will go like this, like this. Okay, if you want to see how it actually looks like in Desmos, then it will, this is sine hyperbolic function, and this is the cos hyperbolic function. As you can see, it cuts the y-axis at 1. Okay, now let's do for uh, tan hyperbolic function. Tan hyperbolic function is one of the most common asked question. There's a reason for it. We'll discuss that later after plotting the graph. Okay, so tan hyperbolic function, it is what? Sine hyperbolic function by cos hyperbolic function. Okay, so it's e power x minus e power minus x by e power x plus e power minus x. Okay, so to make the things easy, we will multiply the numerator and denominator with e power x, so it will get e power 2x plus minus 1 e power 2x plus 1. Okay, at x equals to 0, what happens? It's it's 1 minus 1 by 1 plus 1, so it's 0. So if we plot it, we'll get this. And at x equals to plus infinity, what happens? It's infinity minus 1 by infinity plus 1, right? So we will so this is basically infinity by infinity form, so we'll do L'Hospital's rule. So we'll differentiate the numerator and denominator. We'll get e power 2x, e2 into e to the power 2x by 2 into e to the power 2x again, so it's 1. Okay, so at plus infinity, the function goes to 1. Okay, so this is 1, so like this. Okay, and at x equals to minus infinity, what happens? It's e power minus 2 into infinity minus 1 by e power minus 2 into infinity plus 1. Okay, so what is this? It's 0 minus 1 by 0 plus 1. Again it's minus 1. Okay, so it goes like this. it, this is the tan hyperbolic. Now do you uh, can you figure out where did you see this function? This was asked in IISc interview. Can you identify this function? Where does it occur? We we find this in statistical mechanics, in uh, condensed matter physics, in magnetic systems, for 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 spin half systems. This is how magnetization varies with d by t. Okay, So in Desmos, this tan hyperbolic function looks like this. As you can see, this is exactly 1. So this point is actually 1. This this goes to 1. Okay, this y-axis is 1. We'll do co- cosec cosec hyperbolic x, sec hx, and cot hx at the last, or maybe in the next video. Okay. To illustrate another example, let's take the function y equals to e power 1 by x. Okay, what happens at x equals to 0? Let's do at x equals to infinity plus first. So what happens? It's at x equals to infinity, it's 1 by infinity, so it's 1 by, this is 0, so this is 1. Okay, so at x equals to infinity, the function goes to 1. Okay, this is 1. At x equals to minus infinity, what happens? E minus 1 by infinity, so e 0, so again it's 1 plus 1. Okay, but at x equals to 0, what happens? Y by I'm sorry, e power 1 by 0, so it's infinity. As I said, now since it diverges at x equals to infinity, we'll try to um, we'll calculate what happens at 0 plus and 0 minus also. So at 0 plus, okay, at 0 plus, what happens? It's above just above the x equals to 0 line at the on the right hand side, so it's plus infinity. Okay, so it goes like this. Okay, but at x equals to 0 minus, which means little bit on the left hand side, what happens is it's 1 by 0, so it's e power minus infinity. Okay, so it's 1 by e power infinity, so it's actually 0. So it goes like this. Okay, saturates at again 1. This is y, this is x. Now a similar example, which I will do in the next video, you can take it up as a homework, is that of cot hyperbolic x. Okay, do it as an homework. Another example would be that of y equals to x minus 1, x minus 2 by x, and also y equals to 1 by x squared minus 1 by x cubed. If we are given product of two functions, sometimes the problem might get easy or might become difficult also. Let's see an example of x sine x. Okay, so how does sine function look like? So it looks like this, right? And how does x look like? The just x, y equals to x, so it looks like this. Okay, so if we product the two functions, then we'll simply get a function that keeps on increasing, right? So it will look like this. Again, since this is both are negative, so we'll get something like this, right? Again, because this is a even function, we can just plot on the left hand side and can rep, may take a reflection on the right hand side. Now if the function is x, let's say sine x by x, have you seen this function anywhere? This comes in uh, YDSC or or diffraction formula. So how we will do that? Uh, we can think of it as a product of 1 by x and sine x, and remember that this is a even function, so we'll only plot on the right hand side. Okay, so how does 1 by x graph look like? Looks like this. And how does sine x look like? It looks like this. Okay, so what we'll get is mm, is something that looks like this. It decays in amplitude. Okay, this is 1 by x, not exactly this, but you get how it looks like, how it behaves. Okay, uh, right now what is this value? What is this value? At x equals to 0, sine 0 by 0. So this this is undefined. So we'll use L'Hospital's rule again. So we'll get cos x by, this is x is again 1. So cos 0. So 1. At x equals to 0, this value is 1. The full graph will look like this. This is an even function, so we don't need to worry about it much. If you want to see in Desmos, then this uh, green function is the sin hx, sin x by x. 1 by x is the purple one, and sin x is the red one. Okay. Okay, now another very important function that is very important in physics is that of of x e power minus x square. What is e power minus x square? What is this? This is just a Gaussian function, right? And what is x? X is just x, right? So how does it look like? X is this. And how does e power minus x square look like? It looks like mm, at, at this one, at x equals to 0, it's e power 0, which is 1. And yeah, and at x equals to infinity, it's e power minus infinity, which is 0. So it looks like this. Okay, since it's an even function, it will just take a reflection of it. Okay, so what happens is that at near the origin, this the x part dominates, so we'll get a linear part, and after a while this exponential term dominates, so we'll get this part. Okay, initially this x behavior, and after that we'll get the exponential behavior, so we'll get a behavior like this. Okay, on this side also we'll get a behavior like this. We can do it more analytically. At x equals to 0, x e power minus x squared goes to 0, so this. Okay, at 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 x equals to plus infinity, we get x e power minus infinity squared, which is 0, which is this part. And and again try to understand that since it goes to 0 at x equals to 0, and again at x equals to infinity, there's probably a maxima or a minima. Okay, so we'll take a differentiation minus x square by dx. We'll get some value, and this is the point of maxima. Okay, we'll get 2 points actually at minus x naught and plus x naught. This is minus x naught and this is plus x naught. So the overall behavior will look like this green curve. Okay, if I draw it more clearly, then it will look like this. Now this is very important because this was asked in JNCSR interview. Where did you find this curve? So this curve is the first excited state or n equals to 1 for harmonic oscillator, quantum harmonic oscillator. Okay, now another very important curve is, this was asked in IISER Pune interview. It's y equals to minus x ln x. Okay, so what how does it, if I want to do just purely yeah, analytically, where are the zeros of the function at x equals to 0 and at x equals to 1, because ln 1 is 0. Okay, so here and here. Okay, so since you can as I said, it's cutting the function, it's cutting the x-axis twice, so there has to be a minima or a maxima. Okay, so we'll try to find the minima and the maxima. Again an important thing is that for at x equals to 0, y at x equals to 0, what we get, 0 into minus 0 into ln 0, which is infinity. This goes to minus infinity, sorry. Okay, so what is the value actually? We'll do this by taking by writing the function like this, minus ln x by 1 by x. Again, this is minus infinity at x equals to 0, and this is also infinity. So we'll get an infinity by infinity term. So we'll take Hospital's rule. So we'll get minus 1 by x, and this is minus 1 by x squared. So this is x. So at x equals to 0, we get value 0. Okay, now if we take differentiate, now if we try to find the point of maxima, what we'll do is take the derivative, minus x ln x. So it's minus of x1 by x plus ln x. So this is 1 plus ln x, and this is equals to 0 since it's a point of extrema. So ln x equals to minus 1. Okay, so x is e power minus 1 at 1 by e. Now we can just, from this we can figure out one thing, which is that it's at now, now at x equals to infinity, at x equals to plus infinity, what happens is that it's y equals to minus infinity, and ln at infinity is also infinity, so it's goes to minus infinity. So it goes like this. Okay, so there has to be a maxima and not a minima, right? Because as we can see, there's only one point of extrema we are getting, so there has to be one maxima like this. Okay, and this is 1 by e as we obtained here. Okay, now this graph is very important because this is the graph for uh, entropy. S equals to minus p ln p. This is entropy formula, and p is the probability. Not so commonly asked function is that y equals to x cube minus x square, or functions like this. Not so asked, but still we'll do so that our concepts get more clear. So first we'll Now what is this function? It's even or odd. If we write put minus x in place of x, what we get is minus x cube minus x square. So this is neither this nor this, so it's not even nor odd function. Then we'll try to find the zeros of the function, or where the function cuts the x-axis. We'll simply take square common and write x minus 1. So the function is 0 at x equals to 0 and x equals to plus 1. So it's cuts here and cuts here. So obviously we can say that there's extrema in at this position at between x equals to 0 and x equals to 1. So we'll try to figure out what's the extrema, positions of extrema. We'll just do dy by dx. What we get, 3x square minus 2x equals to 0 at x equals to x naught. Okay, so 3x naught square minus 2x naught equals to 1. So at at 0, sorry, x naught, so we'll take x naught common, so 3x naught minus 2 equals to 0. So x naught equals to 0 and x naught equals to 2 by 3. So this position at x equals to 2 by 3, here 2 by 3 will get an extrema. We still don't know if it's a maxima or a minima, so we'll differentiate it again. Okay, so what we get is 6x square minus 2 at x equals to 0, we get minus 2. So at x equals to 0, it's a minima. Okay, and at x equals to, so sorry, the concavity is upwards, right? So it's maxima. And at x equals to 1, at x equals to 2 by 3, sorry, we get uh, what we get, it's 3 2 by 3 square minus 2 into 2 by 3, which is positive. Okay, so we'll get at a minima here like this, a maxima at this point, and it cuts the y-axis. So since there's no extrema here, so it goes to infinity and this goes to minus infinity. So this curve looks like this. Okay, we can easily figure out what's this value by just putting x equals 2 by 3 at y. Okay, at this function. Okay, so take this as a homework. The function x4 minus x square as a homework. Now I think I made a mistake in the beginning um, for finding the extremas and minimas. If I don't remember, so just remember that if if d2y by dx square at x naught, which means at the point of extrema, is positive, then we get a minima or concavity upwards. Okay, and if it's negative, then we get a maxima. This is minima, and we get a maxima, which means the concavity is downwards. Okay, let's learn a very small concept. So if the function is given 1 by x plus 1 plus 2, how we'll plot this? So as we know, if you just plot 1 by x, then what is 1 by x plus 1, or only this term? It just shifts towards left, right, like this. And what is x, and what is this function plus 2? It's the shift in the positive y-axis. So we'll just shift this green line by 2 units in the along the y-axis, so like this. Okay, So if we plot this in Desmos to make things easy, so we'll just switch them off. What is 1 by x? This is 1 by x. This will just take the first quadrant. What is 1 by x plus 1? We'll try to make another plot. Okay, so it just got shifted to the right, to the left, right? Now what we what is plus 1 by x plus 1 plus 2? See, the purple plot just went up by 2 units. Okay, if we just want to visualize, and what we'll do, look, when n is 0, which means just 1 by x plus 1, this is the black curve. Now if we keep on increasing n, as we can see, the function is going up up up. As we go to n equals to 1, or this term becomes 2, then it just got shifted by unit of 2. Okay, to make it again more simpler, let's do it in plus n. Okay, when it's 0, n is 0, it's just the 1 by x plus 1 function. If we keep on increasing, if when it goes to 1, the plot gets shifted by 1 unit. When it goes to 2, the plot gets shifted by 2 units, and so on. Okay, and we can use this principle everywhere, right? Another small important concept is that of mod functions. Um, Mod functions. So the property of mod function is that the function is always positive, which means if y equals to mod x, it means that at x greater than 0, the function would be x, and x at x less than 0, the function would be minus x. So if you plot it, we get on the right hand side for x greater than 0, which is this side, it's just it's you can say this is y equals to x, and this is y equals to minus x. So we can say y equals to x, this is just uh, a straight line which has y-intercept 0 and slope of 1, and here the y equals to minus x, the slope is minus 1 and y-intercept is still 0, so it would be like this. Okay, now what will be y equals to x minus 1? Again, this is mod, so it's at x greater than, for x minus 1 has to be 0, right? So x equals to 1, y would be x minus 1, and at x minus 1 less than 0, the function would be minus of x minus 1. Okay, so this is minus x plus 1. So if we plot the function, we'll get something like this. This is x, this is, sorry, so it's since it's x minus 1, at x equals to 1, this is this, and here. So this can be easily done by the shifting property. Since it's x minus 1, the y equals to mod x curve will be just shifted by 1 unit towards right, because it's minus 1. Okay, now if we want to plot y equals to mod x plus 1, what we'll do, it will just shift upwards by unit 1. Okay, we can also do this analytically, like like for x greater than 0 it will be x plus 1, and for x less than 0 it would be minus x plus 1. Okay. And a little bit complicated problem would be that of x minus 1 mod of x minus 1 plus x mod of x plus 1. Okay, so this first term would be positive for x greater than 1, and in this case this first term would be x minus 1 for, and it would be negative for x less than 1, and in this case it would be minus of x minus 1, so minus x plus 1. Similarly, this would be positive for x greater than minus 1, and the function would be only the second term would be mm, x plus 1, and it would be negative for x less than minus 1, and the function would become minus of x plus 1, which is minus x minus 1. Okay, so now to plot the function, we'll divide the x-axis in three regions. Okay, x minus 1, minus 1, x plus 1. Okay, so these three regions. So, and and in x less than minus 1, which is this portion, this one, we get function x plus 1. Okay, and x less than minus 1, it's minus x minus 1, minus x minus 1, this one, and x greater than x minus 1, we get, this is for here to infinity. Okay, and for x less than x greater than minus 1, we get x plus 1. This starts from x minus 1 and goes to infinity. Okay, and for this one, the first term, for x greater than plus 1, for x greater than plus 1, the function is x minus 1, and for x less than minus 1, we get minus x plus 1. So the overall function in this region is minus x minus 1 from this one, and plus minus x plus 1 from this one. Okay, I hope you are understanding, because we get these two terms in x less than minus 1 region. So overall what we get is this plus 1 minus 1 gets cancelled, and we get 2x minus 2x. Okay, and in this region from minus 1 to plus 1, the functions would be minus x plus 1, this one, and this one, plus x plus 1. Okay, so so minus x plus x gets cancelled, and we get 2, and in this region it's x minus 1, this and this one, plus x plus 1, so we get 2x. Now if we write it in a cleaner format, so x equals to minus 1, x equals to plus 1, in this region it's minus 2x, so we get something like this, because the y-intercept is 0 here. Okay, Now in this region, in the middle one, it's just 2, and in this region it's 2x, so it would be like this. Okay, so this is the overall function. Okay, so these are, I covered most of the formulas, sorry, expressions. So most importantly, you should practice x ln x minus x ln x also plus x ln x plus x ln x, then x e to the power minus x square, because it comes in harmonic oscillator. This comes in thermodynamics, and also tan hyperbolic x, because this comes in magnetism, and also dielectric actually. So these are the most important ones. For practice, I would also give some problems, like you may practice x mod x to the power mod x, then um, then you can try mod of x minus 1. So there's two mods here. Then 3 comes exponential sine x. Okay, then you can try x square minus 1 square, then e power minus x square, then y equals to e power x by x cube. Okay, then sine x square, sine sine square x by x square. Also 8 would be 3 power x minus 2 power x. Then y equals to 1 by x square minus 1 by x cube. Then would be x to the power 1 by x. 11 would be mod x power 1 by 3. Then 12 would be x minus 1, x minus 2 by x. Also try x plus 6. This is the 13th one. X minus 1 by x minus 1, x minus 3, sorry, and x plus 2. You can also try tan hyperbolic x square, then ln of ln x, and that's it. I have covered all the concepts, and you can do all of these questions using those concepts. Okay, thank you.